Yes, we're recording. All right, so let's begin.
Wait, it's not focusing.
Okay. So how was the quiz? It was hard, right?
Why'd you do that? Why'd you do that? Does this one not count?
I feel like, give him 5 extra minutes.
You're evil.
I was walking around, I didn't know it. I feel your pain. It was hard for me too. Like writing the quiz, I was like, okay, there are like so many questions I could have asked, and they were all great questions to ask. And I couldn't decide. Like, okay, I'm just gonna write down my favorite problems and put them on the quiz. I had like 63 problems. Okay, now I have to cut them down, and that's what we ended up with. So.
Are you gonna curve the quiz?
Okay, we are in section
6.2.
Still 6.2 because it's stupid Trig stuff.
Homework questions though.
No, we didn't finish. How are we gonna?
We 6.1.
6.1.
I didn't even remember I had homework.
Oh.
Okay, 6.1. Questions?
15. Integration of x e
X e
to the power of 2x
2x
divided by 1 plus 2x whole square.
1 plus 2x all squared.
Yeah. dx.
That's crazy. Maybe I should have put that on the quiz. Okay, who tried that one?
So we said u equal to x e to the 2x.
U equals x e to the 2x.
Sure.
Yeah.
Interesting.
The answer, right?
That was totally obvious. Okay, and then the dv was
1 plus 2x.
Same.
and this means your du was what?
Product was so e to the 2x plus 2x equals x.
And your v was? Huh?
Negative 1/2, 1 plus 2x.
Negative 1.
32.
1 plus 2x to the what?
Negative 1
Times
over 2 times 1 plus 2x.
Okay.
So now you do the u v minus v.
And so this is I is equal to, all right, do by parts, u times v. Minus
E to the 2x.
integral of v du. E to the 2x plus
2x e to the 2x
2x e to the 2x.
over 2 times 1 plus 2x. And then over there you can like factor out e to the
Right.
2x, and then just cancel it.
Here you could just factor out an e to the 2x. You'd have an e to the 2x of 2. You have 1 plus 2x over 1 plus 2x, which are going to cancel, and then you just integrate e to the 2x over 2. So we have minus x e to the 2x over 2 times 1 plus 2x. Plus, what is this?
1/4 to the 2x.
1/4 e to the 2x.
Plus c.
Yep. So it's by parts, but the parts were kind of weird. Happens sometimes. Other questions?
27. Cosine, integral cosine radical.
Cosine of radical x dx.
Started.
Yeah. What did you do?
U is further.
I started with u equals cosine radical x.
Oh.
U equals
Then
cosine.
what is v? Then u is square root x.
How would that work?
And then
Wouldn't your du have a sign in it?
Yes, I
How are you going to get that in there?
was confused.
U is radical x.
U is radical x,
And u squared is.
which means u squared is x, which means 2u du is equal to dx, which means this integral becomes cosine of u times, instead of dx, I now have 2u du. Since I suppose you want to do by parts, u is probably a bad letter to use, but the principle is the same. Let's use t. So ultimately, this becomes the integral of 2t cosine t. And that becomes, you can do by parts. So by parts would give us what? All right, so basically in by parts, it said u equals t, du equals dt. You can have dv equals cosine t, v equals sine t. All right. And so it's u times v minus the integral of v du. Integral of sine is
Negative cosine.
minus cosine, which changes this. And now we back substitute for the t. T was radical x, so this just becomes radical x, sine of radical x, plus cosine of radical x. Incidentally, on the quiz, I think I put e to the radical x. The same process would have worked. You would have simplified, you would get like t e to the t or something like that. And then you just do by parts. What's the other one? Any other question?
Could you still have done the same question without doing like this derivative equals x and just went straight to integration by parts?
Without doing this part?
Like without doing all of that, just go straight to the integration.
Yeah, but you'd have to figure out what the parts are.
There is only one part. What's the other part?
What do you mean? Like do, if you were going to do integration by parts with this, probably what you'd think of is saying u equals this.
That's what I tried.
But then v is 1, doesn't mean it's the same thing.
And then v would be 1, which when you integrate you get x. But the thing is, when you differentiate this, you're going to get a sign in there,
Negative sine radical x.
right? And then when you're going to multiply, you're going to get x times sine radical x somewhere. It's going to get uglier. Without doing this, your parts would be something like u equals... Yeah, it'll be hard to see that. You'd have to say u equals something like... You'd have to throw a radical x in there somewhere. The substitution helps you see it. Basically, you'd have to think of this as something like radical x over radical x. And then you can throw the radical in, the u in there, but it would be really weird to see it that way, I think. But you could have done this and then jumped straight to there, but I think it will be more of a headache. You'll basically end up with something like that anyway. So
Number 9.
that's the better way to do it.
Integral of ln 2x plus 1
2x plus 1.
dx.
Okay, so we know that u is equal to 2x plus 1, du is equal to 2 dx. So we end up with 1/2 times the integral of ln u dx du.
Wait, isn't your u ln 2x plus 1
Yeah.
whole thing?
Why?
Because you,
Then we can take b as 1, I think,
yeah.
or something.
I'm not doing by parts. I'm doing a substitution.
Yeah.
Oh,
Because we have the integral of ln memorized. Of course. Right, so this comes u ln u minus u plus c. So it's 1/2 times 2x plus 1 ln of 2x plus 1 minus 2x plus 1. Okay, you can pass your homeworks up. Let's finish here. Let's do more than one way to skin a cat. So basically, this has always been true, but now you'll start to see it more apparent once we broke them through 6.1 and 6.2. What I mean by this is often you'll have several ways to attack a particular integral, and you can be correct in doing it, approaching it several ways, and your answers can actually look quite different. I just want you to appreciate that, sometimes you shouldn't freak out and be like, the answer in the back of the book doesn't match with your answer. It doesn't necessarily mean you're wrong. So I just wanted to point that out. So let's look at an example. Something like sine x times cosine x. Right? There are a couple ways you can do this. One, you can notice, the double angle formula, right? You can realize that this is really, one thing you can do is to realize that this is really 1/2 times the integral of sine 2x dx. In which case you can integrate sine. The integral of sine is minus cosine 2x over 2. Let me write it. Right? Perhaps the easiest way to do it. So this is just minus 1/4 cosine 2x. Right? So you could have done it that way. But you could have also done something like this. You could have said u equals sine. Your du would be cosine. Right? You'd end up with the integral of u du, which would give you u squared over 2 plus c, which is going to give you, u is sine, so this is sine squared x over 2 plus c. And this looks very different from that, but it's actually also a correct, valid, completely good answer, right? I could have done u equals cosine. And then my du would be minus sine. And so I have minus the integral of u du, in which case I would end up with minus cosine squared x over 2 plus c. And that is also a perfectly valid answer, right? So this one integral, we can do it a lot of different ways. The answers can look very different, but they're all correct. How do we reconcile this? Well, it just means they all differ by a constant, right? Right? The difference between this and that is just a constant because there's an identity linking these two, right? The difference between this thing and that thing is a half, right? Which is absorbed into that plus c, right? So you can understand that, and you can also break this down into a sum of cosine squared and sine squared, right? Because cosine 2x is cosine squared x minus sine squared x, right? And so answers can look quite different, but they can all be the same, right? Well, they're all differ by a constant, and they're perfectly correct. So I just want you to be aware of that. So you might do it this way, and then in the back of the book you see that answer, and you're like, oh, really, I'm not getting this. You're not necessarily wrong, right? We did an integral, I think, last time, secant squared x tangent x. And in class, what we did was, we wrote this as secant x times secant x tangent x. And we basically said u equals this guy, and so this guy would be your du, and we did the solution that way. Someone pointed out at the end of the class, and it's perfectly legit, it's to say, you know, we didn't have to split this up in the first place. We could have just said, immediately u is tangent, and then your du would have been secant squared. And you'd have done that way, you'd have gotten answers that look slightly different, but they're all equivalent, right? They're just difference by a constant, because you can connect secant and tangent with an identity. And so sometimes your answer can differ by a constant. So just be aware of that. There's more than one way to skin a cat. And as far when it comes to integrals, you'll realize that that is more true than ever. So I just wanted to point that out before we move on. Last time we started talking about trig substitution. We only did one example. So let's do a few more. Right? In that one example, we use like everything we know about trig, like from ever. Right? We used SOHCAHTOA, the double angle formula, like everything, right? That's why you need to know all that stuff. So let's remind ourselves how this works. Something that was on the quiz: expression, substitute, identity. So if you see an expression like a squared minus x squared, what do you substitute? X can be a sine theta, or it's less common, but you can also use a cosine theta. Here, the identity you're taking advantage of is 1 minus sine squared equals cosine squared, or equivalent 1 minus cosine squared equals sine squared. Right? You see the expression a squared plus x squared. What's the correct substitution? A tangent theta, because you're taking advantage of the identity 1 plus tangent squared equals secant squared. If we have x squared minus a squared, what's the substitution?
X equals a secant theta.
A secant theta, because we're taking advantage of the identity secant squared theta minus 1 equals tangent squared theta. Right? So here we have the function minus the constant gives us one thing. Here we have the function minus the constant. Here we have the function plus the constant. Here we have the function plus the constant. Here we have the constant minus the function. Here we have the constant minus the function. So it's sort of thinking of our identities this way. And we did an example, and you can go over that, but we're going to do a couple more just to sort of get this, because trig substitution can be quite annoying and challenging all in one. So let's do another one. What's that, by the way? It's arctangent. Arctangent x plus c. Okay, so let's pretend the sky fell and you forgot that, right? So you're on a test, you see that integral. How would you figure it out? Right, so you see that integral, the first thing you think, can I use the power rule? No, we cannot. Can I use substitution? No, that wouldn't work. Why? Because if I were to do substitution, what would I substitute? The 1 plus x squared. In which case, the derivative would be 2x, and I don't have an x anymore. So substitution wouldn't work. So now I'm like, okay, what's the next thing? Trig substitution, right? Why? Because the bottom looks like 1 squared plus x squared, which reminds me of this. And so I would do a substitution. X equals 1 tangent theta, which means my dx would be derivative of tangent. So this means my integral would become what? 1 over 1 plus my x is now tangent, so this is 1 plus tangent squared times secant squared. What's 1 plus tangent squared? It's actually secant squared. So that cancels, we just have to integrate the number 1. Which just gives us theta. And what's theta?
1 times
You have to figure it out using the triangle.
x over 1 times
No, we don't need the triangle in this case.
arctan of x.
Just arctan, right? You have x equals tangent theta, you solve for theta by taking the inverse tangent. And so that's how you get tan inverse plus c. More examples. How about this one?
Just radical through that and say it's like a sin theta and stuff. Yeah.
Right, it looks like a secant, right? We have the x squared minus 3, right? So, run a final, we see this problem, what do we think?
Substitution. Trig.
Can I use the power rule? Right, that's the first thing you always think. Can I use the power rule? No, I can't. Okay, what's the next thing you think? Substitution, right? If you were going to do substitution, what would you substitute?
X squared minus 3.
X squared minus 3, the guy that's under the radical. The du would be
2x.
2x.
No x.
We don't have a 2x, right? So we can't do that. And so now we think, okay, what else can we do?
Parts.
I think integration by parts or something like that. That looks nasty. So we think of here, trig sub, because I noticed this guy, the x squared minus a constant, which I can think of x squared minus 3 as x squared minus radical 3 squared. So now my a is just radical 3. And so my substitution would be radical 3 times, according to this table, because it looks like this. Dx
Secant x times.
So what would the integral end up looking like? I have 1 over, what's x squared?
3 secant squared.
3 secant squared times the radical of,
3
what is
secant
this?
squared minus 3.
Because you have 3 secant squared minus 3 times, the dx is this guy, radical 3 secant theta tangent theta. Now we can start to simplify. What can we do here? Well, one of these secants would cancel this, one of those guys, right?
Cancel square root 3. Radical 3.
What does this part become?
Radical 3 tan theta.
Right. Inside the under the radical, we'd have 3 tangent squared, right?
3 times.
So this would become radical 3 times tangent theta, right? That's why we do this trig sub, to combine the terms here. Times here, I have that radical 3 tangent theta. The tangent cancels, the radicals 3 cancels, and so I end up with 1 over 3 secant. How do you differentiate, integrate that? I have 1 over 3 times the integral of cosine. 1 over secant is cosine. And let's continue over here. And so what do we have now? Integral of cosine, 1/3 sine theta plus c. So that's our answer in terms of theta, but that's not good enough, right? Because we were asked the question in terms of x. How do we get the answer in terms of x?
Or secant of x over the square root.
Right, now since I know that x is equal to radical 3 secant, what does that mean? X over radical 3 is equal to secant, or in other words, radical 3 over x is equal to cosine, which means I can do a triangle with theta here. Cosine is adjacent over hypotenuse, so that means this is adjacent, that's the hypotenuse. This side by Pythagoras' theorem would be x squared minus 3, which you will notice was in the original. You should get something like what was in the original. And so then I know that sine theta here would be what? Opposite over hypotenuse by SOHCAHTOA. So this would be x squared minus 3 all over x. This means the final answer is 1/3 times x squared minus 3 all over x. Any questions?
About the table. In the a squared plus x squared be x equal a cotangent there?
You could. Yeah, you could. Because you know that 1 plus cotangent is cosecant squared. 1 plus cotangent squared is cosecant squared. It's very uncommon to do that though. Most people usually use tangent. Did you get this? Or? Yeah. More examples. Basically, we're doing a bunch of examples for you to understand that you'd never want to do this. Avoid if possible. Okay, so here's one. X squared plus 4x plus 8. How would we do that one?
It's just you factor it, like, you know, make it smaller. It's a plus b whole square kind of thing.
Does that factor?
Never mind. I thought, no.
It doesn't factor. So what do we think? Well, the first thing I have to tell you, can I use the power rule?
No.
Obviously
No,
not.
no.
Can we use substitution?
It's trig.
No, right? Okay, so you're like, okay, maybe it's a trig sub, but how do you get a trig sub in there? For a trig sub, we need to have that form. One of those 3 forms. Is it possible? Just look at the x squared plus 8 and then forget about the 4x. What do we do here?
This is a new, I know it's a, I do it from the homework, it's a completing square.
Completing the square. Back to algebra again. How do you complete the square of this?
I just don't know how to complete it. I don't know how to do it.
Let's complete the square. How do you do that?
You just take the whole bottom, x squared plus 4x plus 8 equals 0.
Split the 4x.
Can you add 4x?
We forgot.
Crash course is completing the square apparently. Okay, so we have 4x plus 8. You want to complete the square, what do you need for a complete square? The constant term must be what?
8 times 4.
Give me a formula for the constant term.
4.
B.
No. You look at this coefficient here, and what do you do with it? You take half of it, and you square it. Right? That's how you complete the square. Now you're adding something that wasn't there, so you just subtract it again, right? 4 over 2 squared plus 8. Right? So you just throw that constant there. Of course, 4 over 2 is just 2, right? But what's going to happen when you do that? The first three terms will be a complete square. It's going to be x plus the guy on the inside, all squared, right? On the outside, you're going to have 2 squared, which is just 4, minus 4 plus 8. So you just get plus 4, right? So this becomes x plus 2 squared plus 4 by completing the square. Now can we do a trig sum?
No, why did you? I mean, I know it's basic, pretty tough, but I forgot.
Remind yourself. Don't worry, we'll be doing complete stuff all the time.
Okay, yeah, that's good.
Okay, so now what?
Easy, we just substitute this one.
Now do a trig sum. What does a trig sum look like?
The first one is x. So, oh wait, I don't know.
Intel figure. Intel figure.
Okay, so what's the equation? What do I do?
X equals 2 to x plus 2.
Oh, right. A is our 4, so A is 2, and
A is 2, right? Because this guy looks like
x is x plus 2.
this x plus 2 squared plus 2 squared. So our A is 2. Okay, what's the x?
X plus 2.
Okay, so what's the substitution? X plus 2 is equal to 2 tangent theta. This means I can do dx is equal to 2 derivative of tangent secant square theta d theta. This means I can go and I can plug this guy in. So this here, of course, this is going to become 2 tangent theta, which means that this is going to be the radical of 4 secant squared times the dx is 2 secant squared theta. So what's going to happen here? The radical of 4 is going to cancel the 2.
And then 1 secant left.
I'm going to get 1 secant left, which is going to cancel one of those. So I just end up with the integral of secant. What's the integral of secant? ln of
Secant x plus tangent.
secant x, secant theta plus tangent theta. Okay, but of course that's not good enough because they were asked the question in x, so we must tell them the answer in terms of x. So how do we figure out how to go back to x? Triangle. We know that x plus 2 is equal to 2 tangent theta, which means tan theta is equal to x plus 2 over 2, which I can think of as opposite over adjacent. And therefore I can make a triangle where this is theta. Opposite should be x plus 2, adjacent should be 2, and then this would be the radical of x squared plus 4x plus 8, which is going to be the original guy. And so now this means if I wanted to figure out, for example, what is secant of theta, remember secant is hypotenuse over adjacent.
Yeah.
So that's going to be this guy, x squared plus 4x plus 8 over the adjacent, which is 2. And I already know that my tangent is just x plus 2 all over 2, which means that the final answer is going to be ln of, I can write secant x squared plus 4x plus 8 all over 2 plus the tangent, which is x plus 2 all over 2 plus c. However, for a problem like this, in the back of the textbook, probably what you'll see as the answer is this.
Yeah, not the point.
How would they get that?
2 are, common factor, denominator. So it's just like adding it. Yeah, and then squaring it.
Right, because what you have here is ln of x squared plus 4x plus 8 plus x plus 2 all over 2.
And logarithm rule.
Right? And there's a log rule that says we can actually break this up.
Minus ln2.
Minus ln2 plus c. But ln2 is a constant, so they just call that another plus c. Right? So be aware of things like that. Right? So you might, there's no answer in the book. It's equivalent. Right? The plus c just has the ln2 built into it. So yeah, you have to remember things like completing the square.
Okay, so that.
Any questions on that one? More examples. Yay! How do you do that one? That's right. You can look at this as the radical of 2x all squared plus 1.
So it's just 10.
So what are we going to do? What's the equation?
Should we just take 2 x's as a? So.
No, the a is going to be the 1. A is always a constant.
Okay.
So it's 2x equals tangent theta, which means that 2 dx equals secant squared theta d theta. Or in other words, dx is equal to 1/2 secant squared theta d theta. Which means I can get my integral now. If I put 1/2 secant squared theta d theta, that takes care of my dx. The denominator would be what? This is a tangent. Tangent squared plus 1 gives me secant squared. So this is going to cancel one of those guys. Again, you're going to get secant. This is just 1/2 times integral of secant. Integral of secant is? Then we're going to do the trick. Did we use that one before? We did this before somewhere. Okay, so here, this trig says, okay, so here we have this. Since tangent theta equals 2x, I think of this as 2x over 1, where this is opposite. That's adjacent. So I have a triangle, where this is theta. Opposite is 2x, adjacent is 1. This guy would therefore be 4x squared plus 1 by Pythagoras' theorem. So this gives us the answer. The secant of this, secant theta would be hypotenuse over adjacent. And then the tangent would just be 2x. Questions on that one? More examples. What do you do? Give up.
Wait. Okay.
Huh? X equals tan theta. Dx would be secant squared theta d theta. Right? So now the integral would be, we'd have secant squared theta d theta, replacing the dx. On the bottom we would have x is tangent. Tan squared plus 1 gives us secant squared, but that's the 3 over 2. So this square is going to cancel that. I'm going to end up with secant cubed in the bottom. So there's a secant square is going to die, and then we're going to have 1 over secant, which is cosine, which is integral cosine sine theta plus c. How do we find that? Since I know that tan theta is x over 1, I can have a triangle. It is here, opposite, x, adjacent, 1. This would be the radical of x squared plus 1. This means sine theta is actually equal to opposite over adjacent, which means the final answer, opposite over hypotenuse, so this means the final answer is x over the radical of x squared plus 1 plus c. Looks easy. Until it's on a quiz, then it's like the hardest thing in the world. Questions? More examples. Make sure you go home, you rewatch this, and you try the examples on your own before. Pause the video and try the examples on your own. Because I think most of you have seen the phenomenon by now, how sometimes, oh, it looks so easy in class, and then it's on a test, and you're like, I don't know what to do. It was so easy. That is a completely normal reaction. The thing is, you know, hindsight is 20/20. You see me here up on the board, oh yeah, you just do this. You know, it's a psychological trick. You're gonna feel, oh yeah, that's fine. I don't need to study or do the homework. That was so easy. And then when you go at home to do it yourself, it's a completely different thing. You know. So yeah, it looks easy, but you need to practice. That's why we're doing tons of examples. Make sure you go over all of them.
Can we just like inverse this?
No. Okay. Can we do the power rule? No, we can't.
No,
Can we do
it's
substitution?
It's trick.
Not gonna work. Okay, so now what?
X equals a secant theta.
Oh, expand the square, the square thing.
X
No,
equals
no,
a
no.
secant
Create a
theta.
square out of nowhere. No, never mind. That makes sense.
I don't know what you're trying to say. Okay, so what do we do? X equals
Sine.
secant. This is like it calling out every trig function. Yeah. So dx would be
Okay, now it's easy.
radical 3 secant theta tangent theta d theta. Okay, so at this point, this is something that's going to be important. It's going to save you a lot of headache. Change the limits. Right? Always do this. When doing a definite integral. by trig substitution. Why? It's going to save us from doing all of this, right? We don't need to figure out what the trig functions are doing at back substitute, because the back substitution process in a trig substitution can be really tedious. So we don't want to have to go back and do all this. So what we're going to do is once we rewrite it into the trig function, change the limit so we don't have to go back to the original variable in order to plug things in, right? So in general, I don't care if you change the limits or not on random definite integrals, but if you're doing a trig substitution, I highly recommend that you change the limits. It will save you a lot of trouble. Cut your work in half almost. Okay, so let's change the limits. Original is x. When x is 2, what does that mean for theta? This would mean 2 is equal to the square root of 3 secant theta. This means 2 over radical 3 equals secant theta. This means radical 3 over 2 is equal to cosine theta. This means theta equals, you're supposed to know,
Yes.
is that right?
Where's the sheet?
Who says it's pi over 3?
Where's the sheet?
I'm trying to find something to throw. It's going to take a vote.
Someone take out the sheet.
When does this happen?
1, 2, 3, 4.
Is that pi over 6? All right. Remember, in the cosine, there's 3, 2, 1. The 3 happens in the first one, which is the 30 degrees, which is pi over 6. So you should probably be able to jump from here to here in your head, but you can write this out if you want. When x equals radical 3, what do we have? This means radical 3 is equal to radical 3 secant theta, which means that cosine theta is actually equal to 1, which is theta is equal to, you can do it 0. And so our new integral becomes now, I'm going to actually change the limits. This goes from 0 up to pi over 6. And now let's start plugging these guys in. This guy, x squared, is going to be 3 secant squared. Secant squared minus 1 is tangent squared. So under this, I have 3 tangent squared. My x itself is radical 3 secant, so I'm going to have radical 3 secant times my dx is radical 3 secant tangent. So radical 3 secant cancels the radical 3 secant. At this point, this becomes radical 3 tangent times tangent. So I get radical 3 times integral of tangent squared. How do we integrate tangent squared? Tan theta minus theta. What do you mean? Alright, we do an identity. This is just secant squared minus 1. What's the integral of secant squared? It's just tangent. What's the integral of 1? Theta. This is going to be between 0 and pi over 6. Right? So remember, at this point, if I didn't change the limits, I'd have to go figure out what is tangent, what is theta. I get an inverse trig function and everything. Right? But at this point, now we can just plug these numbers directly into the theta. Let's move it over here. So we get radical 3 tan theta minus theta between 0 and pi over 6. This is radical 3 tangent of pi over 6 minus pi over 6 minus tan 0 minus 0. Tan of 0 is 0 minus 0, so that whole part is 0. We don't have to worry about that. What's tangent of pi over 6? Right, radical 3 over 3, or 1 over radical 3, minus pi over 6. Another example. Main takeaway from that one, trig substitution when on a definite integral, always change the limits. Which means you have to know the values of your special trig functions. Ideas?
Isn't this x equals a sine theta? Let me just use that one here. So a would be.
There's an x attached to the 4. Complete the square. How do you complete the square of that thing? How does it work? You have to factor out the negative. You can only complete the square if the coefficient of the first guy is a positive 1. Okay? And now you complete the square inside the brackets, right? So this is x squared plus 4x plus, what do we add? Half this guy squared minus half that guy squared plus that's it. So what's going to happen now? By doing this, your first 3 terms become a complete square. It's going to be x plus this guy, all squared. X plus 2, all squared. Here, 2 squared is 4, so that's just a minus 4. This is inside the brackets. What does the integral look like now? Four minus x plus 2 all squared. Can we deal with that one?
So x plus 2 equals.
X plus 2 equals
2 sine.
2 sine theta. This means dx equals 2 cosine theta d theta. This means the integral becomes 1 over the radical of. This is 4 sine theta, right? So 4 sine squared. So this just becomes 4 cosine squared times 2 cosine squared cosine theta. So the 4 cancels the 2, the cosine squared radical cancels this. I end up with the integral of 1 d theta, which is theta plus c, which is?
You have to do the triangle again.
You don't need the triangle. When it's just theta alone, you never need the triangle, right? You know that sine theta is x plus 2 over 2. How do you solve for theta? Right, theta is the sine inverse of that guy, x plus 2 over 2. So this is sine inverse x plus 2 over 2 plus c. finish off, I just want to remind you of something. We'll end here. So this ends 6.2. So the homework for this is due on Thursday. Remember, if there is an odd power of x present elsewhere, and my x here just means the variable. You notice here it can be like x plus a constant or whatever. Present elsewhere. Do substitution. We use them. Right? Otherwise, right, this is after you go through your hierarchy of checking for power rule and substitution and all that. So the idea here is something like USub is better. How to do trig sub. Darn it. So something like the integral of x cubed over the radical of x squared plus 4.
Split the x cubed.
Right? Or x to the fifth over 4 minus x squared. Right? Like all these, I'd use a USub because there's an even power. There's an odd power. If it was x squared over this, over x squared plus 4, you're like, darn it, probably use the trig sub. Right? Or x to the 6 over 4 minus x squared. Or something like 4 minus x squared dx. There's actually a nicer, easier way than doing a trig sub here, which we will actually learn about next time. But this is just an example. Partial fractions, that's the next section. You can actually do that with a partial fractions. I asked about that in the quiz bonus problem, but unfortunately we didn't get to it today. But next time we will do partial fractions, which is another integral technique, which I still prefer it over trig sub whenever possible, and sometimes it's, yeah. We will end there. Homework for 6.2 due on Thursday.
Professor.